So everyone, it's a pleasure to have with us Dr. Deeksha Adil, who has been a junior fellow at Institute of Studies with ETH Zurich since January 23. She focused on developing fast algorithms with provable guarantees for problems in optimization, machine learning, and theoretical computer science. She completed a Ph.D. at the University of Toronto under the supervision of Sushant Sachdeva in August 22, after which she was visiting the University of Michigan in the fall of 22. Prior to that, she earned a BSMS in mathematics from either Pune in 2017. Today, she will tell us about optimization and fast data structures. So, over to you, Deeksha.
Thank you everyone for coming. Today I'm going to talk about how you can use things from optimization and things from dynamic data structures to give even faster algorithms. We'll talk about this in the context of infinity regression, and let's see what we can do with this. So more than the results, I want to focus on how these techniques apply to regression. So first, let me give a brief overview of what's happening in the area of fast algorithms these days. So
let's just click on the slide. Yeah, now the focus.
yeah, okay. So basically the goal is still the same. You have a lot of data which you need to do something about. So you need to analyze things, and these data sets are often changing, with the changes being much smaller than the size of the data. People usually try to do four things. They basically want four things. First is you want really fast algorithms, and you ideally don't want to have algorithms that need more than linear and time of period. So it can be algorithms for any analysis task or anything you want to do. You should be able to handle changes into the data quickly. So if you have 10,000 nodes, you have 100 nodes changing, you shouldn't have to recompute certain quantities that you want to maintain. And then you ideally want to prove that it returns the right answer, and hope that it's also fast in practice. People usually think about these four goals when they think about fast algorithm, and different parts of the community study different things. If people in optimization look at these frameworks which try to minimize the number of, let's say, iteration combinations of different tasks. Dynamic algorithm people try to look at changing data sets and see what they can do with it. And there are people who look at sketching and falsification, which basically try to represent these data sets succinctly so you preserve certain properties. And more recently, people have started looking at these things together. For a long time, all these three goals were kind of studied independently. And in Simon's last year, Aaron has given a nice talk about how we need to use these together. So you can refer to that. So some of the recent developments, which include linear time max flow algorithm from 22, where basically use all these three things together. They've used the linear programming framework from optimization. They've used a lot of dynamic shortest path algorithms or data structures, and they've also used some stratification to get a linear time algorithm. Even the state-of-the-art linear programming algorithms have used everything together. And some of these regression algorithms also tend to use a lot of optimization and some data structures together. So today we're going to talk about this very recent work with my collaborator Shunwal, and Rasmus. And this is about how we can use these things together to get efficient algorithms for infinity regression. Okay. So let's look at let's set the stage and notation for regression that we want to look at. So the task of regression is simple. You have n data points in d-dimensional space. And what do you want to do? So if these are your data points, let's look at this represented as a matrix, an n times d matrix with, let's say, some labels to each data. What you want to do is, given these points, you want to figure out which curve fits the data the best. And the easiest task among this is when you have a linear relationship among the data, which is basically what people look at in linear regression. And this is one of the easiest tasks, but we'll just focus on this now. So in this, you'll use a linear regression, and the standard techniques, they try to minimize the L2 norm of the error. And this is easy to do. It's the same as just solving one linear system in transposing. So that people know how to do. Now you can think about, instead of minimizing the L2 norm, different applications might ask you, okay, let's try to minimize other norms, or like some other functions of the error. And some of these commonly used functions could be the softmax function, which is often used as a smoother version of infinity regression. It's also used for matrix scaling kind of applications. You can look at logistic function. This is used for classification, I guess. You can also look at, instead of the 2 norm, we can think about minimizing the p norm. P can be greater than 2. So today I'm not going to talk about these functions, but whatever algorithms I present, we believe you can kind of extend it to this. The same idea should follow because they all have a lot of similar properties. They can work together. So you might ask, okay, these two are specific examples. Let me give one example why people might look at the p norm function. And
So the last one should be the p norm of y.
yeah, it would be the p norm of y. Yeah. So people have so one example is in graph-based semi-supervised learning. So let's say you have a graph with 10,000 nodes, and you only know the labels for 5 nodes, and you want to learn the labels for the remaining nodes. So one way to do this is you put this, look at some, you can train some Laplacian kind of problem. You can try to minimize different norms of the error. And usually when you try and minimize a smaller norm of the error, what happens is all the labels are kind of to be 0, and then you get some spikes along the labeled vertices that you have. And if you try to increase the norm, then you get a smoother interpolation. So a lot of people use these for some of
I
these
don't
things.
understand the problem. So here, what is given to us?
So you have like a graph, you have labels. So you want to find labels associated with every vertex or and let's say you have very few known labels, and based on that you want to interpolate for the remaining graph based on something about it.
Vertices have labels.
Yeah, the vertices.
And what are the constraints on these labels? Like, are the ideas?
So the constraints just come from the graph. The graph is basically the constraint based on what the edge is looking at.
Oh, I see.
Yeah.
Okay.
So yeah, this is one way where people use these different values of p. But today let's just focus on infinity norm regression because these algorithms look a lot simpler. And when you try to look at exact solutions of this is actually equivalent to linear programming. It also captures max flow, but now I guess this is not so important because we know how to do it in linear time. And we don't really know how to solve this in linear time. So let's look at this. So we can think of solutions to the infinity regression problem in 2 regions. You can either think of it as, so you ideally might want to solve it to high accuracy, which I'll describe now. So which is basically that you want to find an epsilon approximate solution, but you hope that your runtime is some polynomial in n is the larger dimension of A. So we're not looking at anything where you can improve this to the smaller dimension. Let's look at the easier case. And you hope that you convert to the error at a rate of log 1 by epsilon. So this can basically let you solve to a 1 by poly and accuracy without losing too much. So we always hope for algorithms of this kind. But let's also consider a relaxed version, which is what we'll call a low accuracy solver. So instead of looking at a log 1 by epsilon solver, you'll look at something that has a poly 1 by epsilon rate. And of course, you can do a lot more with these, and let's see what we can do with both.
Is the previous one equivalent to the exact solution setup?
Yeah, in some ways. So if you think of matrices which are polynomially conditioned, then it's almost like an exact solution.
So in that first style of with the smoothing, you should probably care about the gradient and not the Laplacian. No, you're taking the p norm of the gradient and not the p norm of the Laplacian.
So this is some experiments that's done by some other people. What they do is they just take the p norm Laplacian. So it's something like, so Laplacian can be written as a quadratic form.
Yeah.
Instead of the quadratic form, you
Okay,
take the p powers and you try to do that. Okay. So getting back to the high and low accuracy, so let's see what we can do with both these settings. So in general, the most popular schemes for infinity norm regression kind of look like this. So you have a bunch of iterations. Each iteration solves a weighted linear system or a weighted least squares problem. And based on the solution, you update your weights and you build your solution. And in the end, you just return some value, some function of the x that you have built so far. So most of these popular algorithms, including interior point methods, can somehow, some multiplicative weight update methods can be made to fall under this very general framework. And if you look at this, what takes, if you want to optimize the runtime, it's basically you can think of two things. You either have an iteration complexity, so you either improve the iteration complexity or you look at the time that the algorithm takes per iteration. So if you try to decrease the iteration complexity, which is what we term as acceleration, and this is what most optimization people study. The other thing you can do is you can decrease per iteration. First is what for which you would need some data structures. And the most common data structure is what we call inverse maintenance, and we'll describe this in more detail a little later. So for now, we'll just think of inverse maintenance as something, think of it as a black box that helps you decrease the per iteration. And let's see how have these tools being used. So if you look at the high accuracy algorithm, these have been proposed from the 1940s. So the first was the simplex method, which has an exponential runtime, but it's really fast in practice. So people sometimes still use it. The first polynomial time was the ellipsoid algorithm, which was 10 to the 6 in runtime, but it was worse than the simplex algorithm in practice. And then in the 80s, there was a method by Karmakar which inspired the interior point methods, and there has been a long line of work on interior point methods and what even with in terms of data structure, iteration complexity, people have considered things like that. So the interior point methods, I'm not going to talk about the method, but I'll say that the iteration complexity that we know is you need root n log 1 by epsilon iterations. Each iteration solves the least first problem or solve the linear system. So in general, you need something that's the number of iterations times n to the omega. So this is roughly the time you would need. And to improve this, iteration complexity is a long-standing open problem, and we don't know any lower bounds or even upper or like any better upper bounds than root n, even for special structured matrices. For graph, maybe you can do better, but in general, we can't. And there have been many works on improving the integration complexity using inverse maintenance for interior point methods at least. And the state-of-the-art inverse maintenance data structures, they can improve it to n to the omega plus n to the 2 plus 1 per 6. So this is a deterministic algorithm. And if you allow randomization, you can do it in this because you plus 1 of the using these data structures. So in terms of low accuracy solutions, a very simple multiplicative weight update routine, which just solves a linear system in each iteration and hopes to find the optimizer of an infinity regression problem, that still requires root n iterations. And of course, if you apply these data structures that you apply to the interior point methods, we get the same runtime. But we can additionally accelerate this iteration complexity to cube root of n. And the first work that did that was a paper on max flow by Cristiano Keller, Spillman and Teng in 2010, where they used electrical flows to find the maximum flow, and they were able to do a very similar kind of acceleration. Okay, so in this case, we can accelerate this. One may naturally ask, can acceleration and inverse maintenance be used together? They should directly give you a faster algorithm. And we'll see that you can do that, but it's not as easy as it might look at. But yeah, the short answer is you can accelerate, and we'll see how we can do that. Okay, so before we do that, let's look at what people do in terms of acceleration or what we know about acceleration. So the first schemes were proposed by Nesterov to accelerated gradient descent in the 80s. And since then, there have been many other schemes, many more generalizations.
I got a bit confused. If you go back to the previous slide.
Yeah.
Yeah, so didn't you say a slide ago that square root of n cannot, nobody knows how to improve it?
Oh, that's for
Polynomial.
high accuracy. High accuracy.
Oh, high accuracy.
So this is the low accuracy region.
I see.
So you're relaxing this.
Got it, got it. Yeah, fine.
Okay. So in terms of acceleration, there have been many schemes that are being proposed. Some of these are parallelizable and you can customize these to different settings. They give you similar rates, but it's kind of tricky to use any of these schemes with any kind of data structures. So what we will look at is a similar scheme based on the multiplicative weight of data routines. And these ones are, what we know here is the first one was for infinity regression, which will actually be extended to LP regression, and you can even extend it further to Hessian stable functions. You can read this as Hessian stability, which means that the Hessian of a function doesn't change too much when you have two points that are closing. And these algorithms are at least compatible with some kind of data structures. And there has been one work that one of our previous works kind of combines inverse maintenance in a very naive way, but it doesn't even make the easier law of deterministic. So it's not quite useful. But yeah, so at least we know these are somewhat compatible with data structures. So we look at these.
Sorry, so you're saying these do have acceleration?
These do have
And
acceleration.
your question is, can you have,
Can you also use data structures
Okay.
like these? Okay. So yeah,
and
this-
these papers were the first ones to show acceleration using end of multiplicative weight updates?
yeah, these were the ones to kind of show something for LP regression. And improve so you can actually do high accuracy LP regression with acceleration. But you can't do high accuracy infinity regression. So in this case, the P kind of has to be bounded away from infinity. Okay. Yeah. Yeah. And in terms of what we know for inverse maintenance, this has also been studied for a long time. And it was first again, it has always been studied in the context of interior points.
So in the multiple iterations, the the problem is solved in each iteration. Are they completely different? Are they related? The linear systems, are they related to each other?
They're kind of related in the sense the weights are related every time we're solving it. So
Weights,
okay, right. So instead of thinking of it as a linear system, if you think of it as a weighted least squares regression, say you're solving something like weight times some xe squared. Okay. So these weights are related, and without the weights being related, you can't cope.
and data, intuitively, how does a data structure for what? Does it help us thinking?
Yeah, we'll look at that in more detail right after.
I'm confused about the motivation a little bit. The pictures that you showed before, they were suggesting that for P that is larger than 10, nothing really changes.
Yeah, you don't get too much more improvement experiment.
Yes, exactly. So why would you want to get faster at infinity if you already have faster at P?
So infinity is a kind of an independent thing. One hope would be that if you can do faster infinity directly, at least in high accuracy, that's equivalent to linear programming. In one.
Why is that? I mean, if you're just optimizing and the result does not change, why not optimize for LP, which you can do fast?
But you said the LP algorithm, the runtime depends upon
If
P.
the runtime depends linearly on P. So if you want to do infinity using that, so you can go to P equals log n over epsilon. That directly gives you a multiplicative approximation for the infinity regression, but that already gives you a polygon by epsilon.
No, I'm saying just put P equals to 10 because it did not change beyond 10.
For that particular example, it changed, right?
The two-dimensional picture.
That's just one set of experiments, something.
Right.
Okay. So next we want to look at what inverse.
Also, what are so there is also for P less than 2, like 1.
So for 1 to 2, we don't know any direct acceleration. We know that for 1, but anything between 1 and 2, we don't know. And I mean, you can take the dual and that gives an answer.
But that's
Yeah, direct answer. Because what happens is for P less than 2, you lose Hessian still. That's one reason why we can't combine it with you. Okay, so let's look at inverse maintenance, which I've been talking about. And we'll look at the best known algorithms so far, which are by Brand, Nananka, and Saranurab from 2019. So they give a dynamic data structure for for maintaining the inverse of matrix. So So let's see how we're using it first in this general scheme. So what we are doing is you're solving a weighted least squares problem. Or basically what you're solving is this problem. So these R's can be thought of, these are some weights, and then you have a quadratic term. So if the exact solution is just this, which is the inverse of a matrix times some vector. And what's happening is, as you change this R, this matrix is changing and this vector is changing. And all you need for this algorithm is this delta, which is this product, the matrix inverse times the vector. So the question is, if you can just somehow find this without going through solving this, then you're good. That's all the algorithm. The remaining algorithm needs just that. And this exact, yeah, we want to.
Yes, I mean, so this is the only way to, I mean, you have to invert this matrix in order to get to the solution of infinity. Because it's a saddle point optimization problem, right?
Using min max.
It's a min max, right? So min max is just equivalent to a game, and then you can just use cheaper mirror descent, online mirror descent.
So you can do all of that too. That's also
That
one.
will avoid all sorts of inverses.
Yeah, that would, but those methods, those are something based on these gradient methods, that you just take gradient descent. But I'm just going to look at a family of algorithms that are based on taking a quadratic.
But that could be accelerated as well. I mean, those are gradient.
But those acceleration schemes are also, so you can't hope to get a high accuracy solution using just gradients.
So this is you're basically solving a game, right? And there is a very famous paper by Daskalaris. It actually solves this. Not this is a two-player game, but it actually solves a multiplayer game and shows that you can get this high accuracy result. You get regret of the form log t.
But that is the regret again. So
regret is equivalent to your accuracy here because your AI.
Yeah.
The matrix doesn't change, right? So you're not considering matrix A remains the same. It is not changing with time.
But you can solve, but you can't really hope to solve infinity regression as such to high accuracy using just green.
So mean max is will solve linear programs.
So let's solve linear programming. That would be a big breakthrough if you can solve it for less than easy trade.
So this is a mean max. You're basically solving a game, right? It's a mean max game.
So there's also another work
Then
in
should be able to solve it.
linear programming. If you can solve it to high accuracy, that should be able to give a faster accuracy for you.
No, but it leads to a gradient based, simple gradient based tablets that avoids. My main point is that it avoids the inversion state.
Yeah, but I'm guessing it would still have a trade-off somewhere else in the runtime if you're computing gradients or.
Okay.
Because if you could do that, that would give a very fast living performance.
Those things are dependent upon the bit, like
Yeah, that probably
on
also
the size of the entry.
Yeah, maybe that. Yeah, that's also true. These gradient based methods.
Simple to ask. What is being updated? What is the unknown name? You're minimizing over RI or
So you're minimizing over delta. This one, you're solving for delta.
what is being updated now?
So what you update is this. So you use this, the solution you get. You update the R and you update this. X is
So that's some other way of
There's some way of updating which I'm black boxing for now. But the idea is you just want to find this, and the remaining algorithm is also doesn't care how you find this. Okay. So we reduce this to just finding this product, which is the inverse of some matrix that's changing and some vector that's also changing. So the goal of inverse maintenance is exactly this. You have some matrix M, which gets some updates every iteration and some vector. And for every t, you want to return this product. So this is all we want to do. This is all we ask from these inverse maintenance data structures. And let's, for simplicity, assume B doesn't change, but whatever algorithm I say would also apply to when B changes. And that doesn't change. Okay. So this is the easy deterministic data structure of Brand, Ananda, and Sarananda. So let's look at this. So this data structure, it takes an initial n times n matrix n, and it can do two things. One is it can update the matrix. So given some update to the matrix, it can update the inverse from M inverse to the new inverse. And if this delta has some k non-zero entries, or then basically you can, the time required is the time required to multiply two matrices of size n times n, an n by n matrix with an n by k matrix. So if now this should be k. So if you see here, the first thing is if k is equal to n, you're not gaining anything. So you always want to hope that you're not updating the entire, you're not updating the entire size. And the other thing the data structure does is it lets you query. So it outputs this, which is what we wanted. So the new matrix inverse times the vector. And this takes some time, but we can, let's ignore that. That doesn't matter at this point. So given.
It's extremely, it's like you can't even have one entry per row or something.
Yeah. You want to get a really sparse matrix.
Question, is the reset result not more different?
Which one?
The reset result, that if you change the matrix, how many
Yeah, I think these were known, but this just is.
combination?
Yeah.
And in the typical problem statements, how many non-zero entries does delta typically have?
So it can be dense, it can
So
have,
it can be.
it can be dense. But it can be dense, but it can be small. That's the fact we're going to use, that the updates can be small, but it can be dense. Okay. So given this, how do we hope to use this in this framework? So the thing we want to do is every time you don't want to make a full update, because if you do that, you don't win anything. So what you do is you collect updates. So you want to hope that you do a lazy update scheme, in the sense that instead of always updating this, you collect a lot of updates, and once you've collected enough, you do an update.
So I'm just curious. I mean, you're basically solving A infinity not problem, right? But
Yeah.
somehow in the inner loop, you're solving L2 problem,
Yeah.
right? So I mean, what is the connection between these two? I mean, is it just it works or there's a deeper?
Okay, good. So if instead of thinking of infinity, if you think of LP, let me talk about that. That's a little easier to look at. So if you write minimize LP norm, minimize X P norm to the P, and let me think of this as a fixed point problem. So instead of minimizing X P norm to the P, if you think of the minimizer. So let's say the minimizer is X star, and now write this as a fixed point iteration. So this is the same as minimizing some X star to the P minus 2 times some delta E squared. And if you minimize this problem, it gives you the same answer. So I mean, it's just one way to do it because people know how to solve linear systems. You can also think of, instead of solving L2 problems, L4 problems, L10 problems, all of that's fine, but it's just that we don't know how to solve those efficiently. But I'll also talk about that in the very end, that if instead of solving L2 problems, you solve some L10 problem, can you get a better iteration complexity, and what's the optimum in that? So that's also something we can prove, and we did very recently done that. Okay, so let's get back to this. So, so what we want to do is we want to utilize our inverse maintenance procedure, where you don't want to put a full update. So we do a lazy update. So you basically can update, but you don't update. You just collect some updates or coordinate-wise updates. And the way it helps, and so there has to be a reason why you can collect these updates, because even if you are supposed to update it in every iteration and you're not doing it, then that shouldn't harm the remaining algorithm. So for that, let's see what all we need from the algorithm. So the first is, let's look at the unaccelerated version. So you have root n iterations. Every iteration requires one query operation because you want your vector delta, which you can use to make updates. And to be able to do the lazy updates, you need some stability property in the iterates that, okay, every time every time you can do something like large updates happen very infrequently, or something that you can collect updates in a good way. So that's what we call as stability.
So
And
update is one coordinate.
one coordinate wise update. So you can collect that, and all coordinates are updated very infrequently. And you have a lot of small updates many times. So the algorithm thankfully satisfies the stability property, and even interior point method satisfies the stability property. So let's think, so what this means is that for any L, so let's say L is something between 0 and log n. So every 2 to the L update iterations, you do an update of size 2 to the 2L. So what this means is at the end to these root n iterations, you're doing an update of size n. So that you can make a lazy update scheme that kind of that follows this. And from the data,
In the interior thing, you will go off the central path if you don't give the right gradient, right?
right. So this is not the centering step. We're still talking. So in that you also need to do additional centering steps. So let's ignore that for now. Just talk about the feasibility steps where you're solving something.
Okay.
So and this is all for low accuracy. So for now, let's so the interior point one is actually quite I mean, it just uses in principle it just uses these data structures with that. But to actually formalize this, they still needed to write something for about 100 plus pages to actually get the details of all these entering steps and things like. But the base idea is just basically this.
Can you go back to the result that was during the delta, like the time complexity?
The inverse maintenance.
No, further back. Like this one, yeah. K0, K0 is supposed to be K. What exactly is T and K?
Oh, this is just the time required to.
Yeah, how much is it?
For now, just think of it as the n to the. I mean, for simplicity, just think of this as we'll just use this to the n squared. Just for simplicity, think of omega equals 2 and we'll just call this n squared. Otherwise, it's a little involved calculation.
How is it defined? You're multiplying a n cross n matrix?
N cross N
N
with N
cross
cross
n
K.
with an n cross scalar.
Wait, but in n to the omega, I can always multiply to n cross n matrix.
Yeah, this, I'm just using, I'm going to use a very conservative bound for now. The exact bounds are.
So you will not use the fact that all you're using is that K is at most 10?
Not in the final runtime, but when I'm going to look at a simple case when omega is 2, in that I can do this very crude approximation that you can do 2 n times n matrices in n square time.
But wait, you can't do 2 n times n matrices in n square time.
If you can do it in to the omega, I'm just going to take a simple case that omega equals 2 and also.
No, my question is, so I'm trying to see where the improvement comes from. One thing could be that because multiplying n times n with n times k is faster than multiplying 2 n times.
So that the final runtime actually uses that. You get that improvement. That's one reason. The other reason you get an improvement is the stability. So you're going to amortize. So I'm going to get to computing the runtime.
Good. So
You're going to amortize. You're not going to, because of the stability, you only need to do this some fewer number of times. You can divide it by something.
okay, so if you get an improvement from here and you also get an improvement for stability,
Then you get something like.
Like K naught is small compared to n. right?
Yeah, usually it's like 10 or n to the 2. I mean, you'll basically, yeah, that was the next point in this slide actually.
So that is that's faster than doing Sherman models in K times.
So the proof of that is exactly Sherman.
Okay,
Yeah. So the proof of that is this. So the simple deterministic one is exactly Sherman. Okay,
but my question is if you only do one of the two, either you do the stability trick or you do the theorem that you had before.
exactly. You get half an improvement, you won't get the full improvement, but you get some.
You will get something less than half.
Yes.
Okay, yeah.
Okay. So these were the runtimes. So you try to think of, you have some query time. And let's say I'm collecting into the A0 objects and I'm going to set some parameter. So the reset time was this rectangular matrix multiplication. Let's look at omega equals 2. So the reset time just requires n squared from the matrix multiplication. You have root n iterations. And from the stability, you only have to do this, you can amortize this over a few. And in the query time, you just query every time and you crudely multiply it with the number of iterations. Just balancing these terms directly gives you the n to the 2 plus 1 over. So this is the, and the same kind of analysis can apply to interior point methods, at least the inverse maintenance part is simple. So just doing this, and if you only had stability and you didn't use any other fancy thing, then you just get 2 plus 1 over 9 as. Oh, wait, actually I'll get to that even later.
I have forgot what it says,
Oh no, this is just this parameter. I'm just trying to balance out these parameters so you can match, you can kind of balance out these two times. So
Is it connected to the A0 in the previous?
yeah, it's the same. We're just trying to fix the parameter. Okay. So this is the very simple rule returns.
Sorry, I just want to understand this. So, what is the query operation?
So the query operation is what returns the M inverse B situation. So that is what gives you the delta that you want to use to update your weights in the.
I see. And so this, the query estimate here is query across all the square root and.
Yeah, so this is per iteration and then you multiply it with every number of
Yes.
iterations.
But if all we are getting is a vector at the end of it, I mean, should we think of so the output is an
Right.
n length vector,
Yes,
but we are paying n to the 1 plus
Yes,
a
yes.
naught to and we are picking a naught fairly large.
yeah.
I see, and this is still favorable somehow.
So this is still better than what you would naively do, which is n to the half plus.
Because-
Because basically you're saving some time over here, you're not computing the events exactly. Okay, so this was just easy deterministic data structure. There's a more complicated. Okay, yeah, so I missed one thing. So what did we use?
So what was that query type? No, in the VM.
The data structure. Kind of. So you can think of 2A0 plus 1.
So update or in the query space you can delta is also an input.
Yeah.
No, delta and B are both. inputs.
Yeah.
And then once in a while you might just be asking change M completely and then.
Yeah, you can do that. So let's see. So what all did we use for?
And the guarantee in each iteration is that you're epsilon away from the right answer.
Yeah.
In infinity.
Yeah. Okay, so we use two things. We use the iteration complexity. We used our lazy update scheme. And I might ask, is this enough for the algorithm to work? And there's one thing that we're missing out in this is that now because you're not updating this every time, you don't have access to the exact weights that you should have. You have access to something that's approximate. So this requires an additional property from the algorithm, which is what we call robustness. So this just means you have some coordinate-wise approximation to the weights, and your algorithm still returns the right things the right way. So interior point methods are also robust, so that's good. Multiplicative weight methods are also, at least these ones are robust. So everything works well in this. So for the deterministic case, you can very easily get the two plus an accelerated deterministic data structure gives you this 2 plus 1 equals 6. So all of these apply to the IPMs. And now let's look at the more complicated, more involved randomized data structure. So what this does is, instead of directly updating the inverse, it does it in 2 steps.
What is the contribution here? What is your contribution?
I'll get to that. We add acceleration to this, which is kind of tricky.
So far is parallel.
Yeah.
Okay, BNS.
I mean, part of this is also unpacking the paragraph. These are 100 plus page paper. So now instead of directly maintaining the inverse of the matrix, you do it in 2 steps. So you want to collect more updates, update it less frequently, collect small updates and update it more frequently. And somehow they're able to use these 2 things. I won't get into detail because that's also involved. So you update frequently with small changes and collect more and update slowly. And with these 2 things, let's ignore these for now. You can basically get a more involved data structure, which has 3 operations now. So the first reset is exactly the same as the previous one. You have an additional thing which collects the small updates and does it frequently, but this one does it implicitly. It doesn't output the vector. So if you do an implicit update, you can't exactly query the vector. So you do a bunch of these small ones and then you can just implicitly update it. But what we'll actually focus on is the query of this. So in the query operation, you again output L entries of this vector, and this operation can be done in certain time. But let's just focus on the query operation because the other two I just promise that they're well be given this. So we focus on the query. So now this says that if you output L entries of this operation can be done in some amount of time. Now if L equals N, so then this query time is exactly the same as the query time of the previous data structure. So you're not getting any improvement if you output the entire vector. So this is imposing an additional restriction on what you want to do. To get any gain, this is an additional restriction. So you can't just ask to update the entire vector. Like we did before in the update operation, you needed a sparser update for which we use the lazy updates. Here you also can't output the entire query vector. You want to output something that's a sparse representation of this. So with this, so you need some additional data compression tools to get any improvement out of the second kind of this more involved data structure. So you need something, and what's used is they use a sketch of this vector and they use that to make updates. So this is what
Sketch of delta R.
sketch of delta. Or I mean, you can apply a sketching matrix somewhere here and you get some.
It's between delta and sketchable in some sense for that. I mean, do you have control over this?
It should, and for these algorithms it is, which is a good thing. In general, it is not, and that's part of the reason why acceleration is not. And so, okay, so for these unaccelerated things, so this is what the very long paper that does the IPM in n to the 2 plus 1 over 18, it basically uses this. So it uses a sketch with these R's, and for this, they still need stability. You need a much stronger robustness in the R because now you're also introducing an additional error which comes from using the approximate updates. And they can use a sketch of size root n to make the updates, and everything works fine. And balancing out all the terms gives you the 2 plus 1 over 18 result. So all of this very easily, all of this easily translates to the multiplicative weight update setting, which is basically what we were talking about. For IPMs, you also need to worry about centering steps, but let's skip that for now because we can't accelerate them. And for this, we can do a much simpler analysis. So far, what have we seen? We had an optimizer, we have inverse maintenance, and we have sketching. So for the deterministic thing, all we needed was stability and robustness. The inverse maintenance only asks for stability and robustness. And the stronger one also asks for sketching, so that imposes an additional robustness condition on the optimizer. Once you have all of this in an optimizer, you can do something much better than ideal.
I mean, the stronger inverse maintenance plus the sketch improved it from 2 plus
1 over 6
6 to 2.
plus 1 over 18. Yeah. So now let's see what happens when you try to add acceleration.
And the sketching here is what's the goal? Is the sketch has to preserve L norm or inner products?
So the sketch in this sense, it just has to preserve some coordinate wise properties. Like the coordinate wise error shouldn't be too high. Yeah.
So it's implicitly having a large vector, but it's query to give the entity, then it's smaller.
Yeah. Okay, so when we add acceleration, let's first look at an easy version where we use a deterministic data structure. But before we do that, let's look at our acceleration scheme. So I'm going to unpack our updates a little more. So now we look at our updates. So this is the exact weights that we're using, where you update these weights in a multiplicative fashion. And so this is the simple unaccelerated version, or the multiplicative weight, where you just update the weights multiplicatively. To solve the linear system, you use a regularizer. It's simple. And to accelerate this, what we do is you have the same weights, the same weighted least squares problem, and the same updates, except that now you have to use absolute values here because to get acceleration, you need these weights to be kind of increased. And the other thing is, you only make these updates when the infinity norm is small. Otherwise, you don't make updates. And when the infinity norm of the solution that you get is large, you look at the large coordinates and you penalize those weights. So I'm not going to get into the details of why this works, but this has been studied for a very long time and we know that this works. And so basically now what we want to remember is you're using absolute values to get the acceleration in the weights. So you can think of this having two steps, primal steps and weight reduction steps, as it's called in the literature. And what we know is you have some n to the 1/3 primal steps, n to the 1/3 weight reduction steps. And for both of these now, so you need some more properties to make this work. So one thing is that, okay, this particular algorithm is robust. Both primal steps and weight reduction steps are robust, which means you can use approximate weights and everything will still work well. You can also prove a stronger notion of stability, which comes from the acceleration. So that's again a positive thing. And what we can prove is, okay, in every 2 to the L iterations, you can perform an update of size 2 to the 3L. The previous stability could do an update of size 3 to the 2L. So what this means is that these updates can be even more easy, which is also a good thing. So the deterministic data structure showed very well for them. So this is the previous stability that you have. This is a new stability. So this is more easy. So if you want to see what we can do with the deterministic thing, so now you have an improved iteration complexity. Every iteration again queries. You have a stronger stability property. And from the data structure, you can again look at the reset time, which was this matrix multiplication. You have the iteration complexity and some amortization from the stability. And the query time is still the same, just at the iteration from this point. So balancing this gives you n to the 2 plus 1 over 12. So this is one easy improvement, which comes from two factors: better iteration complexity, more laziness in the iterates. And if you remove one of this, if you take the same iteration complexity but the stronger laziness, then you get something that's 2 plus 1 over 9. And if you do the other, you just take a better iteration complexity but the same laziness, then again you get the same 2 plus 1. So getting both gives you some improvement. So far this was easy. All we did was you prove a new stability, make sure the algorithm is still robust and nothing fails. So this is good. So you can prove that there's a deterministic algorithm that solves it in this time when omega equals 2. And this has a faster rate of convergence. So now what happens when you try to use the other data structure? And that's where things get more complicated. So things here were good. Here are the inverse maintenance, stronger stability, everything to do. So now let's look at the algorithm again. So again, if we recall, we can't have access to the full vector. You need to use a sparse approximation, which we get from a sketch. And when we do this update, now you do the update based on the sketched vector that you have. And we have these absolute values. So the first problem that we get is coordinate wise error in W in the weights has to be very large, because if you use any estimator, forget a sketch, any estimator over here, these absolute values already say that the estimator is unbiased. So any error introduced has to be proportional to the standard deviation of the estimator. And the standard deviation of these estimators is really large. The standard deviation is something that's the L2 norm of the solution divided by the sparsity of the sketch. So the L2 norm from the multiplicative weight of that routine we know is something like root n. So unless you use the full vector, this error in that you get from this standard in the weights is quite large. Okay, so this is one flaw. This is one obstacle. So how can we get around this? The main problem is coming from these absolute values. So you may ask, okay, what if we just try to find another accelerated algorithm which doesn't use it? And this absolute value has been key for most of this. So, but okay, we can still find an algorithm. So Madhuri has done something for maximum flow in a very specific setting, and he's able to write some multiplicative weight update routine, which doesn't use this. So if you try to extend that, you can get a nice algorithm which doesn't use this monotonicity weights. So this resolves the issue of large error weights. But what happens is, because of the monotonicity, you were having some kind of controlled weight reduction steps. So
Wait, maybe I'm missing something there. So the issue previously was the fact that because you always have an absolute value, your the variance will always be. I mean, the standard deviation will always show up in.
the error computed in the weights. In the weights, so the weights would deviate from the actual weights by a very large one.
Okay, and what's the plan right now?
So the plan is, can you write an accelerated algorithm without these absolute values?
Okay.
So these absolute values have been key in these multiplicative weight routines
Okay.
to give simple accelerated algorithms. But you can also write a monotone is what we call accelerated schemes. But there's obviously a trade-off. The monotonicity was helping you in some way. Now what happens is you have too many width reduction steps. So this loses all kind of stability in the width reduction. So also the non-monotone algorithm has way too many. So earlier what you had was you had approximately n to the 1/3 width reduction step. Each iteration it was enough to just penalize like one coordinate or a constant number of coordinates. Now what happens is, because of this loss in monotonicity, you kind of have to penalize n to the 2/3 coordinates in every iteration. And then that makes you kind of lose your stability property, because you need to update too many coordinates in every iteration, which will bad for this. Okay, so there can still be a solution. Maybe you can design a new set of width reduction steps that is also stable, also known, and it doesn't have too many updates per iteration. And when you try to do that, there's a trade-off in the iteration complexity, and that trade-off comes out to be something like, instead of 1/3, now you have something like 1/2.5 iterations. So with this trade-off, we can actually design a new set of width steps, which are stable, which are good, at least for the lazy updates. Okay, so what we can do is, you can design an optimizer which has some sort of acceleration. It has some stability, so that's good. All the primal steps, all kinds of steps are stable. It's also non-monotone, so you're not collecting too much error on the weights. But the question still remains if this is robust. So all the previous algorithms were very easily robust. You could take any coordinate-wise approximation and think about any coordinate-wise approximation within a factor, and everything was robust. But for these algorithms, it's actually very delicate, and there's only like a very specific scheme, lazy update scheme with respect to which these turn out to be robust. So they're not robust in general, but you can get some sort of robustness via a specialized lazy update scheme. And this actually depends. It's not even modular, so it's intertwined with every part of the algorithm, which you would really like it to be modular. And when you do all of this, you still run into some small issues that the non-monotone algorithm needs to find some L3 norms and some large coordinates, and you can use some independent data structures for these. So for find some large coordinates, all you do is just run some heavy hitter data structures, and if you want to simulate L3 norm, there are some other sketches which you can use. So all of this together gives us an improvement in runtime. So when you add acceleration, you can improve the 1/18 to a 1/22.5. And this also converges in a better iteration complexity. But the thing I want to highlight is you can actually use acceleration with these data structures and get some improvement in this.
It doesn't, because it was n/3 before. I know to the 1/3, right?
Yeah, but you lose that when you try to make the width steps stable. So the 1/3 version with non-monotonicity has way too many width steps, and those are necessary to get the acceleration. So to kind of stabilize that, you do a fewer number of things per equation. So for this, you can get some improvement to the existing techniques. Okay, so this was the main result I wanted to get to. So are there any more questions before I move to?
Is this? I understand you're saying this for omega equals to 2, but that also means that because we don't have any algorithms with omega equals to 2 so far, in practice, the higher order term would stay the same into the omega.
I mean, you can also write a complete formulation for this. So most of these algorithms can be written as something as n to the omega plus n to the this term.
Yeah.
And then so you can also do this for this, but I think there's some condition on omega. So omega has to be greater than n to the 0. Omega has to be greater than n to the 2.04 or 04 or 0. Yeah.
That's exactly what I'm saying. So if it's n to the omega plus n to the 2 plus 1 over 22.5, it's the same as n to the omega plus n to the 2 plus 1 over 18.
Yeah, for now, but the main idea is there's been a lot of interest in people trying to get something that's exactly n to the omega plus n squared for interior point methods. But
No, I understand that. I
Yeah.
was just, so one of the things you were motivating was fast algorithms in practice. I was
Yeah.
trying to connect it to that. That's fine.
Yeah.
But also, why can't all the inversion steps be replaced by equation solvers, like approximate equation solvers? Which
So if you saw the width reduction framework that I was talking about, the one where you accelerate that can't work with approximate solver.
it has to.
It has to have coordinate wise good approximation. So you can't just do objective values. Yeah. Okay. So yes.
When you say it has to, does it mean there's a negative result or does it mean
It's
it
not, I
at
mean,
least?
so far over the years, people don't know how to work. Yeah. Okay. Okay. So far we saw some inverse maintenance data structures for some acceleration algorithm and how to obtain these fast algorithms for the low accuracy regression and the challenges when you try to use these people. Actually, one more motivation is to get any kind of things in. You at least want to try and use acceleration and data structures together. And so far, there's basically no works. This is relatively new, where you're trying to merge these techniques together. So this is one step in that direction as well.
But how much more time do you think?
Okay, I can quickly brush through these. It's just some of the passwords and such as well. Okay, yeah, so let me just give a quick overview of some of my previous works. And some of these are based on past algorithms for regression. Some of these which might have showed up along the way. And now let's just talk about P non-regression, where P is greater than 2. And by duality, they can work for P less than 2. And yeah. So the interior point methods, they reduce it to root and linear system solves. And this was actually retested 2018. In 2018, Bupek, Cohen, Lee, and Lee, they gave a new method which could do better for small values of P, but it couldn't do better for large values of P. And so this basically matches interior point as P is closer to 1 and infinity, and you can do a lot better for smaller values. So one of our works where the first thing you can actually combine this with a high accuracy solver for LP norms. So which we call an iterative refinement framework, which means that you can write nice global upper and lower bounds for an LP norm function, and you can do some minimization similar to smooth and strongly convex. And you can get an improvement using some multiplicative weight of weight-based methods. So this is the first thing that can get a high accuracy accelerated framework. And it's better for all values of P, not just large values of P, and there's one concurrent word for P equals 4. That does this using a different set of techniques. And some extensions to this, actually they extend to a broader class of functions. And you can, instead of solving linear regression in each iteration, if you try to solve LQ regression, you can get some optimal algorithms, and I'll tell you what the rates are in a little bit. So basically, if you're directly, you want to solve p-norm regression using q-norm regression. If you directly try to do it, you lose a lot in the approximation. And this factor is quite large. But if you try to solve a regularized problem instead, a smooth LP norm, and this is kind of what relates to the previous results where I mentioned you can write global envelopes for LP norms, and the global envelopes look like this. They're kind of like a smooth version. So if you do this, you can so for this, you can solve this using something that's okay from quadratic plus L cube x cube x q norm to the q, and you only get this as an approximation. And this was one of our previous results, and using this, we could give some algorithms for max flow, which at that time gave you an order m over epsilon algorithm for max flow. And then very recently, we can update this to a very similar way that we could do for using linear systems, and kind of gives the same improvement where you have a 1 over q minus 1 over p instead of a 1/2 minus 1 over p. And this is actually optimal. We can prove lower bounds that say that this is the best we can do. So when you try to apply these two graph problems instead, so now you want to minimize some p-norm flow in a graph where you send something from a source to a sink. You apply the same thing, same algorithm. So you can get, so if you have m edges, you have m to the 1/3 iterations, and each iteration solve the Laplacian linear system. So if you use fast Laplacian solvers, you can get something that's like m to the 4/3. But you can actually improve this using some sparsification techniques to something that's linear in m and depends on the vertices, the 4/3 to the vertices. So these are a few things we could do. And in terms of fast algorithms in practice, so we can actually write iteratively reweighted least squares algorithm for LP regression that provably converges. So these algorithms were used in practice, but they were not always guaranteed to converge. And even we know single instances which diverge within 10 iterations for p as small as 3.5 or something. So using some of these frameworks, you can design an algorithm that probably converges for all values of p. That's away from infinity. And they actually are almost 10 to 50x faster than the available implementations to solve linear regression. So these are some of those. And in terms of pure acceleration schemes, there are some things you can do in acceleration via width reduction. You can also do something for smooth, highly smooth variational or like min-max problems in some sense. The generalization which gives you variational inequality problems. And to get the result which solves LP regression using some other solver, some LQ solver, you need to generalize proximal point methods to some other settings. And all of these together give you the absolute results. And you can also, so some more attempts of combining optimization and dynamic data structures. So there's one thing where if you are given a Ph.D. matrix, which undergoes some kind of updates, to the question is if you can maintain the maximum eigenvalue and eigenvector. And this is related to, this is exactly the same as a covering semi-definite program where you have one matrix constraint. And for these things, you can actually maintain the solution in amortized time, which is polylog. And for any other setting, this question is still it's kind of hard. So even if you increase this to one linear constraint and one semi-definite constraint, the problem is still hard, and we don't know how to do it. Okay, so some of the broader open problems in this space. So if you look at this picture again, so what we're going to talk about some broad problems in optimization and some things that can really utilize some dynamic data structure with this framework. So in optimization, some of the things that we still don't know are acceleration in some non-convex optimization settings. The closest we know is something that does this monotone variational inequality, which is still kind of convex, but it's not exactly convex. So any kind of and there's some work which tries to use a restarted accelerated gradient descent and it achieves some kind of acceleration for some structured non-convex problems. And then there's still a lot unknown in higher order optimization. Like what is the real power of higher order oracles, and if you can really implement these higher order oracles efficiently. And then there's still some how much can you accelerate min-max optimization? So there's still quite a few unknowns in these areas. And in terms of IPMs and data structures, the first question may be, can you improve this inverse maintenance scheme? So far we were using something that was working for 2 levels. Improving that even to 3 levels is unknown. But we still believe that if you can improve it to something like log n levels, you can get the n squared plus n to the omega thing. We have everything else also gets limited. So it's also an easier question might be to see if you can get an inverse maintenance that's better for at least special applications or structured instances, or even if you can get some kind of IPM acceleration for structured instances. Because at least you know for LP regression, you have a high accuracy accelerated algorithm, but that's nowhere close to an IPM, to an interior function. Right? So it's still, or if you try to even do something like random matrix instances, as in, can you do something better with that? And in the space of dynamic optimization, there's basically almost nothing. So most of the optimization algorithms are not designed to handle changes in data. People look at online optimization, they look at algorithms, but they all have very different goals. They don't try to maintain a solution when there's change to our data. So in this setting, what we know is we know something about packing positive linear programs. There's some characterization. There's something known for the least squares problem. There's a little bit known for some special box inflex games, and then there's one that can do this positive semi-definite program with one constant. But beyond this, we don't know anything. Even for some very simple problems like smooth and strongly convex optimization, suppose you're trying to minimize some map of AX, where if there's both smooth and strongly convex, try to update A, we still don't know how quickly you can do it, or if you can do it better than recomputing. So these are some easy directions, I think, to begin, at least in this space. And yeah, there's always the question of how would you get fast algorithms in practice. So some of the common issues are numerical precision issues, which is one of the reasons why we can't really implement these. There have been some studies on improving these numerical precision by Richard Penn and Pala and some people, but it's still quite a mystery. And then similar to the simpler LP regression algorithm that we have that works fast in practice, it remains that for other problems you can design maybe some suboptimal in theory algorithms, but some things that run really fast in practice. And if you can prove some kind of error stability bounds to that. So yeah, that's
Maybe we can take like one quick question.
yeah.
So the questions on graphs that you were talking about, where the runtime used to be m to the 4/3 essentially, but then you could specify the graph and then work with the 4/3 is over the number of vertices, etc. What sort of specifier do you need to use here? I mean, like,
so you need to use a specifier that can maintain an objective of the form
some
LP
LP.
squared plus LP to the P.
Oh, the smoothed version
The
that you.
smoothed version is what you need
I
to
see.
maintain. So some specifiers from this other work kind of apply to these settings. So that's one thing you need, and the other property you need is that you should be able to reduce the high accuracy part to a sequence of low accuracy solvers. Because whenever you do a sparsification, you can't get something that's really log 1 over epsilon. You can't maintain the solution to a log 1. So that basically you're using these two ideas. You reduce it to low accuracy solvers. Given these low accuracy solvers, you're trying to sparsify these low accuracy solvers, solve the sparsified version, and then you claim that okay, the sparsified version maintains the solution to a good approximation. And then you go back to your higher things.
And presumably the typical spectral specifier, etc., is not going to be enough for.
No, that can't maintain LP to the P of it. Like the ones based on Lewis weights, that's the extension of the spectral specifiers to P naught, right? Those need something like N to the P over 2 rows also.
Oh.
So that doesn't really help when you sample using those.
Understand the sequence. I think there's a sheet to sign up for slots for faculty and students. So if anybody say wants to sign up, I think there are many slots.
What? How small does the value of omega need to be for this performance to start showing up?
Oh, to upper bounds to start.
I mean, the improvements.
So at this point, it at least has to be less than 2 plus 1 over, okay, 22.5.
Okay.
Otherwise, you're already.
I don't want to be a factor.
Yeah, yeah.